So the first thing we're going to do, recall the definition of work done on an object by an agent that exerts a force on that object. Remember what the formula is? So remember, in the simplest case, it was force times distance, right? Force times some displacement. But if we do we can make it a little more interesting by putting a dot product in there, right? But this is if F is constant. Over that distance. Or another way of writing it is the magnitude of the force, the magnitude of the displacement, and the cosine of the angle between them. Okay? So sketch, draw a little block in there, and sketch an arrow for the force acting on the block, and an arrow for the displacement of the block. That would give us positive work being done by that force on the block. What do you have? Which way is your block moving? To the right? Which way is your force? To the right? Okay, that would be positive work. That force would be doing positive work on the block. How about negative work? It's moving to the right. Which way is your force? To the left. So in the first case, that force would be causing the block, if that's the only force acting on it, causing the block speed to increase, causing it to move faster. In the second case, maybe the block comes sliding in with some initial speed, and we start pushing in the opposite direction, and we're doing negative work on it, and the speed slows down. Maybe it's a friction force, right? The block comes sliding in to the right, there's a friction force to the left, doing negative work on the block slows down. How about zero work? Which way is your block moving? To the right. Or maybe it's not moving. That would cause zero work, right? But if it's moving, what direction for a force? Down or up? I'll draw mine up, I have more room there. That force does no work on that block because it's not changing its speed at all. Okay, now we're pushing a block up an inclined plane, a frictionless inclined plane. So draw a free body diagram for the block. Frictionless inclined plane. Okay, we have a free body diagram. What's touching the block? The hand is touching the block, so that creates a force up the incline. What else is touching the block? The incline. A surface can interact two ways. normal to the surface with what we call the normal force, and parallel to the surface through friction, but in this case there's no friction. And that's everything that's touching the block. What can reach in from a distance and exert a force? Gravity. So I'm going to write a W sub y and W sub x, or you could just draw it straight down towards the center of the earth, either way. All right? And that's everything. Draw an arrow to represent the net force on the block. What direction is the net force? Up the incline, is that right? The incline's a little steep. Okay. Work done on the block by the hand. Positive, negative, or zero? We have agreement? What direction is the block moving? Up the incline. What direction is the force from the hand on the block? Up the incline. It's positive work. They're in the same direction. And remember, it's a good habit to get into when you're talking about work done on something, fill in the blank, by something, fill in the blank, right? Get in the habit of saying it that way. Work done on the block by the hand. Work done on the block by the earth. Positive, negative, zero. Work done on the block by the earth. Let me write this. Negative. Because the y component is doing no work, and the x component is pointing down the incline, and the block's going up the incline, so it's doing negative work. And work done on the block by the incline. Because it's just the normal force. There's no friction in this case, just the normal force. So it's not doing any work. Is there work done on the hand by the block? What do you think? The hand is exerting a force on the block. Are we good with that? The block is moving. So there's work being done on the block by the hand. Is the block exerting a force on the hand? Yeah, that's a Newton's pair, right? If the hand pushes on the block pushes back on the hand with an equal and opposite force. Is the hand moving? Yeah, it's moving through the same distance that the block is, right? It's pushing on the block the whole time. So is there work being done on the hand? Yes. The work done on the block by the hand is equal and opposite to the work done on the hand by the block. They're both moving through the same distance, but the forces are opposite direction. Equal magnitude, but opposite direction. So the work done is the same, but we have a negative sign on one and not the other one. So in this case, so it's yes, and this would be negative, because the other one was positive. Work done on block by hand is equal to the opposite of the work done on the hand by the block, because it's a Newton's pair. Number 5 on the next page, the work kinetic energy theorem states that the change in kinetic energy of a rigid body is equal to the net work done on that body. So explain how your answers in part 3 are consistent with this theorem. Is there net work being done on this block? Is its kinetic energy changing? Yeah, it's speeding up. Isn't that what they told us? It's speeding up. So its kinetic energy is changing. So there has to be net work being done on it. So if we look at section 3, we said the work done by the hand was greater than 0, the work done by the earth was less than 0, the work done by the incline was equal to 0. How would this be consistent with us having net work being done on the box? We know the net work done on the block has to be positive because it speeds up. We know the work done by the hand is positive, the work done by gravity is negative. So which one's bigger? The magnitude of the work done by the hand has to be greater than the magnitude of the work done by gravity. Because the work done by the earth, the work done by gravity, that's negative. Work done by the hand is positive. When you add the two together, you have to get a positive number. So the positive one has to have a bigger magnitude. I think that's all they wanted here. If it was going up with constant speed, instead of increasing speed as it is, if it was going up and at constant speed, how would anything change in number 3? Work done by the hand, positive, negative, 0?
Isn't it still positive?
Still positive. It's just less now, right? The hand's not pushing quite as hard. Still positive. Work done by gravity, still negative. Work done by the incline, still 0. So they would all be the same. The only difference is the work done by the hand would be equal to the magnitude of the work done by gravity, so that when you add them, one's positive, one's negative. When you add them, you get 0. Okay, why did we go through that? Because we're trying to figure out when is our gas in our cylinder doing work, and when are we doing work on the gas in the cylinder. So this next section is going to walk us into that. An ideal gas is contained in a cylinder that's fixed in place. The cylinder is closed by a piston as shown in the diagram. There's no friction between the piston and the cylinder walls. Describe the direction of the force that the piston exerts on the gas. The direction of the force the piston exerts on the gas. What direction is that force? To the left. Can a surface pull on something? No, right? So the only direction that makes sense is to the left, because the surface can't pull on the molecules that come up and bang into it. It can only push on them. Does your answer depend on whether the piston is moving? No, it doesn't matter, right? The surface can only push on something, can't pull on them. So it basically, if a gas molecule bangs into the surface, it feels a force in the other direction, right? It feels a force to the left in this case. It doesn't matter whether the piston is stationary, whether it's moving to the left or whether it's moving to the right, the force is always to the left. Okay? How could the piston move so that the work it does on the gas is positive? To the left, the force and the displacement have to be in the same direction. So if the force is to the left, the displacement has to be to the left. And negative the other way, right? Force is to the left, displacement to the right, we get negative work done. Does your answer depend on the coordinate system? What if to the left was positive? Doesn't matter, right? It's just the relative direction. If the force is this way and the displacement's that way, we have negative work done. If they're in the same direction, we have positive work done. It doesn't matter if it's in the negative direction in our coordinate system or the positive direction in our coordinate system. What matters is the relative direction of those two forces. It's independent of coordinate system. And how do you compare the work done on the piston by the gas to the work done on the gas by the piston? They are equal in magnitude, opposite in sign, right? The work done on A from B is equal to the negative of work done on B from A. Just like the hand and the block. Okay, that's going to be important because some books define the first law of thermodynamics with work done on the gas, and some define it with the work done by the gas. And so what's different in those two equations? A minus sign. So you have to understand which one is which. All right, we will get into that next time. We'll stop here, take a 10-minute break, and then we'll start up lab.